Good afternoon for everyone. First of all, thank you very much for your time and to be here with us for our algebra seminar. So it's my great pleasure to introduce Margalit from Georgia Tech. He'll talk about homomorphisms of Braid groups.
Thanks again for having me here. It's really a pleasure. I'm going to talk about work on Braid groups with Chen on the left and Kevin Kordek on the right. Chen is a postdoc at Caltech. Kevin Kordek was a postdoc at Georgia Tech. So I will get started. Please interrupt when you have questions. I'm happy to answer anything. So this is the summary of the talk. The goal is to classify homomorphisms from the Braid group on n strands to the Braid group on 2n strands. And basically the summary is that we can make a list of all of them, okay? So I'll explain how that works. And also we have another theorem. This is the commutator subgroup of the Braid group. I'll explain what that is. So it's an infinite index subgroup of the Braid group. And we can also classify homomorphisms from here to here. There's two different proofs we use, but either proof can be used to prove the other theorem. So it's kind of, there's various ways to approach these problems. And so I'll show you two ways to approach these problems, but there are others that I'll talk about. Okay, so I think I'll start by just saying a little bit about what the Braid group is. So we'll start there. This is a picture of a braid. Okay, so to form a braid, you take 2 copies of the plane. You take some points in this copy and the same points in the other copy, and you connect them by paths. Okay, that's what a braid is. Now the paths have to go monotonically down, so they can't do a loop like this. Okay, they just go straight down like this. They can end at different points than they start, and they also don't intersect. Okay, so they can tangle just like a hair braid, but no intersections. And we say 2 of these are the same if they're isotopic, meaning you can deform one picture to the other. So if I take this strand on the right and I do this, it's the same braid, as long as I don't pass it through another. Okay, so I don't know how familiar your group is with braid group, Sheila, so please ask questions if you have them. The group operation is stacking. Okay, so if you have 2 braids, this is a braid on 6 strands. If you have 2 braids on 6 strands, you can stack the pictures. Okay, and you get another braid on 6 strands. That's the group operation. Okay, and you can check associativity is not hard to believe. Inverses is also not hard to believe, but you can check all those things. Okay, so that's the braid group. Those are the things we care about. And I don't know. I'll just say the reason you care about the braid group shows up everywhere in math and science. And the reason you care about the braid group is you should imagine, and if you have 6 points moving around in the plane, okay, and you trace out the motion over time, okay, 6 points that never bump into each other. If you trace out the motion over time, if this is the time direction, then you get a braid, okay? And so braids are recording different ways that points can move around in the plane. Okay, those points can be, you know, points, particles in physics, or robots on a factory floor, or roots of polynomials, or whatever you want. And so that's why braids show up everywhere. Any question on the definition? These are the objects we'll be talking about. So please stop me if you have any questions. Okay. So this is a picture of, this picture on the left is a picture of multiplication in the braid group. Okay, this is a braid called sigma 3, okay, because the 3rd strand went behind the 4th strand, okay? And this is the braid sigma 1 inverse, because the 1st strand goes over the 2nd strand. So this index tells you which strand is going over which. So sigma I takes the ith strand under the I plus 1st strand. Okay, and this is the composition. This is the product. Sigma 3, sigma I inverse, sigma 2 inverse, sigma 2 inverse again, etc. So this is how you multiply in the braid group. Okay, and so this is some element of the braid group. one thing that's also being shown here is that these sigma i's are generators for the braid group. If you have any braid, no matter how complicated it is, you can chop it this way so that only one crossing happens at a time. And so that shows that the braid group is generated by these sigma i's, where the ith strand goes past the I plus first. All right. Good. So those are the generators for the braid group, sigma I, sigma 1 through sigma n minus 1. And the relations here, these are the defining relations for the braid group. So if I have, let's say this is sigma 1 and sigma 3, that's the same as sigma 3, sigma 1, right? Because as braids, you can deform one to the other. Okay, so that's a relation in the group, and those are called the disjointness relations. And over here, you have what's called the braid relation, or maybe sometimes they're both called the braid relations. This is, so you should think of this as ABA equals BAB. When you have two sigma i's that are next to each other, sigma I plus 1, you have this braid relation, ABA equals BAB. And it turns out that these are the defining relations for the braid group. Okay. You should think of these as type 3 Reitermeister moves. Okay, so one way you can think about the presentations is you have to understand, if I have two representations of the same braid, how do I get between them? So it should be something like the moves in knot theory. Okay, these aren't knots, they're braids. And these pictures were made by Esther Dalvit, who wrote a very beautiful thesis on braid groups. Okay, I think those are the basics about braid groups. A little bit more, I guess. A theorem of Fadel and Neuwirth says the braid group is torsion-free. That's not hard to believe. Here's the argument why. So braid is you tangle some strings together. If you keep doing the same pattern over and over again, the strands get more and more tangled, right? So if you have an element of the braid group and you multiply it by itself a number of times, the braid does not come undone. You know this from if you ever braided hair. If you repeat the same pattern over and over again, the hair does not fall apart at the end. Okay, so that's a theorem. The braid group is torsion-free, and one proof is that the braid group has a finite dimensional KG1 space. Any group with torsion, any group that has a finite order element, a KG1 space will be infinite dimensional. So here there's a nice KG1 space, which is you take this is maybe a simpler way to say it. You take the space of configurations of n points in the complex plane, and that's the KG1. Okay, so this is what I was saying on the first slide. You can think of a braid as a loop in the space of configurations. So you have points in the plane, they move, and they come back to where they started. That gives you a braid. That's what this is saying. Okay. So anyway, this is the fact. The braid group is torsion-free. That will come up later. Another way to think about the braid group, which is the way I will be thinking about it mostly, is using mapping class groups. So when you have a surface S, MCG is the mapping class group, and it's homeomorphisms of the surface, identity on the boundary, modulo homotopy. So for the braid group, you take the surface to be a disk with n points marked in the interior, and you look at homeomorphisms that are the identity on the boundary that fix this set of points, and you mod out by homotopy, but the homotopies fix the boundary and fix the set of points. And that's the same as the braid group. So a braid is the same as a homeomorphism of the disk. And one way to think about that, I like this picture on the right, again by Esther Dalvit, is you can take this disk here and put it kind of up here at the top of the braid, okay? And then if you pull the disk down, the braid mixes the disk around, okay? You can think of it, it'll stretch the disk, and that gives you a homeomorphism of the disk. The more sophisticated way to say it is if I have a braid that's a motion of points in the disk. And so you can think of that as an isotopy of a zero manifold and a two manifold. And you can extend an isotopy of a zero manifold to an isotopy of the whole disk. And at the end of the isotopy, you have a homeomorphism of the disk, or even a diffeomorphism. So any questions on this correspondence between braid groups and mapping class group, which is really homeomorphisms of the disk, or anything else?
Mapping class group is the group of automorphism of a surface, right?
Ah, very good point. The mapping class group is the group of outer automorphisms. So when you have a closed surface, the mapping class group of a closed surface is, and maybe you should allow orientation preserving, but it's basically out automorphism pi1 SG. It doesn't quite work for the punctured disk because the fundamental group of a punctured disk is a free group. And so it's a subgroup of the outer automorphisms of the free group. It's the subgroup that preserves the loops, the conjugacy classes of the loops around the punctures. But yeah, so this is that's a good point. It's a good way to think about mapping class groups algebraically, just how they act on pi1 of the surface. Yes. That's the Day-Nielsen-Baer theorem. Okay, so so that's an introduction to braid groups. Again, the question is, what are the homomorphisms between braid groups? Okay, so first of all, there's this beautiful theorem of Artin from, I think, the 30s, maybe 40s. Okay, so Artin, 47, classified all homomorphisms from the braid group to the symmetric group. Okay, there's an obvious homomorphism from the braid group to the symmetric group, because if you have a braid, you can ignore the crossings, and it gives you a permutation, right? This is the permutation 1, 2. Okay, so that's the obvious homomorphism from the braid group to the symmetric group. And he proved that every homomorphism either has cyclic image, or it's this homomorphism, possibly post-compose. You can always post-compose with an automorphism of the symmetric group. But that's what he proved, that all homomorphisms are of that form. And he asked about homomorphisms from the braid group to the braid group. More specifically, he asked about automorphisms of the braid group. By the way, his theorem up at the top uses Bertrand's postulate. So the deep number theoretical fact that between n, you choose any number n, between n and 2n, there's a prime number. Okay, that's called Bertrand's postulate, and somehow his proof uses this. So he asked if there was a proof that did not use Bertrand's postulate, and today, until today, that's not solved. Okay, but anyway, we have this theorem. Okay, so basically, the question on the previous slide is Artin asked about all automorphisms of the braid group, and so what this slide is saying is I'm going to give you some natural automorphisms, and the theorem is that's all of them. Okay, this is not our theorem. An automorphism of the braid group is geometric if it's induced by F in homeomorphisms of the disk. Okay, so there's really, so if you conjugate a braid, so think of braids as the mapping class group of the disk. If you conjugate by a braid, you're conjugating. If you conjugate by a homeomorphism, it's basically the same as conjugating by a braid. So what's written here is almost exactly the same as this. Because when you conjugate by homeomorphism, you're conjugating by a braid, that's an inner automorphism. Okay, except there's one other kind of homeomorphism of the disk where you flip it over. Okay, flip the disk over vertically. Okay, well, if you have all the mark points like this, and you reflect the disk like this, that's a homeomorphism of the disk. It's not the identity on the boundary. So it's not a braid. There's no braid that does that. But it's a homeomorphism of the disk, and it induces this automorphism of the braid group. Okay, sigma I, all the sigma i's go to sigma I inverse. Okay, it's like switching left and right. Okay, and so when I say that's everything, that means that's all of the geometric automorphisms, are either conjugation or replacing sigma I with sigma I inverse. Okay, those are geometric because they're coming from homeomorphisms. A priori, an automorphism of the Braid group is an algebraic object. These are the geometric automorphisms. And the theorem, this is from, I think, the late 70s, 81, it says on the slide. Okay, the theorem is that all automorphisms of the Braid group are geometric. Okay, so every automorphism of the Braid group is induced by homeomorphism of the disk. To say it another way, it's basically an inner automorphism, possibly modified by replacing all the generators with their inverses. Okay, it's a beautiful paper. I mentioned at the bottom some of the ideas that go into it, but it's a beautiful classic paper. I highly recommend. Any questions on the statement of the Dyer-Grossman theorem? Basically, we're generalizing this, right? They understood automorphisms, Bn to Bn. Our work is to understand homomorphisms from Bn to B2n.
Yes, I have a question.
Yes.
So geometric automorphisms is just semi-direct product of Bn itself and cyclic group of order 2, is it correct?
Exactly, correct, yes.
And how many conjugacy classes of cyclic group of order 2 this group has? Is it infinite, finite?
Wait, can you ask the question again?
I mean, we have semi-direct product, Bn and cyclic group of order 2, right? It might have up to conjugation many torsion or can have few torsion. I mean.
Oh, good question. Yeah, that's correct. The only torsion is the Z mod 2. And
yeah, but
no, sorry. There are infinitely many conjugates. Yeah, infinitely many conjugates. Yeah, basically, the way you get an element of order 2 is you should draw. So there's an element of order 2 that flips along that line, and if I draw a more complicated, well, I won't make it too complicated. So topologically, the orange line is the same as the purple line, but since it's all topological, I can flip along the orange line. And so, and that's a different, that will be a different automorphism. And there's a question, and hopefully that makes sense. So the outer automorphisms, yes, that's correct. The outer automorphisms do not lift to automorphisms of B6. I believe that's correct. I guess it follows from this. But I have to think about it more slowly. Good. Any other questions? So, so the theorem of Dyer-Grossman is automorphisms of the Braid group, and this was extended. Bob Bell and I, this is I think the first paper I wrote as a postdoc. Bob Bell and I classified all injective homomorphisms from the Braid group on n strands to the Braid group on n strands and even n+1 strands. So there's an obvious homomorphism, which is just inclusion, right? If you have a braid on n strands, just put one more strand on the side, and that's an inclusion map, okay? And our theorem is that's basically all of them. Okay, they're all geometric again. And Castel, in his thesis, he's a student of Louis Paris, generalized this in two ways. Instead of just injective maps, it's now just a homomorphism, okay? And instead of n+1, it's n+2. Okay, so when you classify homomorphisms from Bn to Bn+2, you're also classifying homomorphisms to n+1, because if you had a weird homomorphism from Bn to Bn+1, you would then get a weird homomorphism from by including into Bn+2. Okay, so those are the main ones. Down at the bottom, I mentioned some other ones, but automorphisms of the pure Braid group and other versions, but the main part for the talk is just these at the top. Okay, and as I said, our theorem is to try to go up to 2n, or change the n+2 to 2n. Okay, all right. So that's expanding the range. Oops, you can't see that yet. expanding the range. Okay. All right, so here are some, when you go to 2n, there's more interesting things that can happen. Okay, so here are some homomorphisms. You have the trivial map, obviously. You have inclusion. You can just send sigma I to sigma I. So basically the last n strands are doing nothing. You have diagonal inclusion, where if you have a braid in Bn, you just do it twice. Okay, that's a homomorphism. There's also flip diagonal inclusion. Given a braid in Bn, you do that braid on the left and the mirrored braid on the right. And that's a homomorphism. Okay. So those are some things you can do that you can't do until you get to 2n. Or you need 2n for these two. But also you have cablings. The cabling is when you have a braid in Bn and you double all the strands. Okay, that's also a homomorphism. I have a picture of that here. So if you the homomorphism that sends sigma I to this cabling. So this is you should imagine 2n strands. These thick cables are just to help guide you. The only strands in the picture are these here. Okay, and so that is so that's a homomorphism. Okay, it's not too hard to see if you think about it. Okay, so that's called a cabling map. There's more complicated cabling maps where inside each tube you allow the number k1 means some number of twisting. So it could be positive or negative number. So inside one of those boxes, it's just looks like this, some amount of winding. Okay, now you can't, if you want a homomorphism, you can't choose any numbers k1 through kn, but they have to satisfy, there's some linear equations you get from the braid relations impose linear equations. But still, there's you get many more cabling maps by allowing this twisting inside each tube. Okay, so the goal with our project is to get a handle on all of these different things you can do. And there's even other things you can do. So if you have a homomorphism from the braid group on n strands to the braid group on 2n strands, again, like with Artin's theorem, you can post-compose with an automorphism of the target. That's still a homomorphism. And there's something a little more subtle called a transvection. Okay, so this here is the center of the braid group is cyclic. It's generated by an element z. It's a full twist of the strands. Okay, and if you given a homomorphism rho, you can modify it by z in the following way. Okay, you take each row sigma I and multiply it by the central element, or even if you want a power of the central element. Okay, that's still a homomorphism. Oh, I see. Z is just some element of the center, so it's the k is already absorbed. Okay, so that's called the transvection. It's still a homomorphism just because the z is central. So if you write down ABA equals BAB, you get a z cubed on both sides, and they cancel each other out. Okay, so so that's the extra mess you have to deal with. You have those other standard homomorphisms I talked about, but then you can also post-compose like this, and you can also transvect, which means you just modify by central element. Okay. Now these operations generate an equivalence relation. So we can say two homomorphisms are the same if they differ by either of these moves, because those are really, they're different homomorphisms, but it's not so different. Okay. So that's, so we say that the two homomorphisms are the same if they differ by these. Okay.
Sorry, Dan, may I ask you something?
Please.
So, but what is the automorphism group of B2N?
That's the Dyer-Grossman theorem. It's the braid group, semi-direct Z2. So the braid group is acting,
right.
B2N now, not Bn, is acting by inner automorphisms and then the flip. So yeah, so we have a complete list of that.
Okay.
So we have a good understanding of this equivalence relation. Yes, thanks for asking. Okay. So here's how our theorem is going to go. We have all these different things you can do, all these cablings, diagonal inclusion, etc., post-compose transvection. The way the theorem is going to go is we list some standard homomorphisms, and the theorem is going to say everything is equivalent to one of these, exactly one of these. So we have the trivial map, inclusion, diagonal inclusion, where you do the same thing twice, flip diagonal, where you do a braid, and then it's the inverse on the other side. And then you have k-twist cabling. And this is a picture of k-twist cabling. So this is a very, remember I said the cablings, you could have different amounts of twisting in every cable. So this is very specific where you only have K twists in the ith cable when you're doing sigma I. Okay, so it's a much smaller collection of cablings. And there's a formula for it here, but it doesn't matter. And the theorem is that for n at least 5, every homomorphism is equivalent to exactly one of these. Okay, so by giving you the K-twist cablings, the specific cablings, all the other ones are equivalent to that one under the equivalence relation I said. So that's our theorem. Yeah, notice it's not true for n equals 4. It's not true because there's a exceptional homomorphism. This is the only time there's a homomorphism, a surjective homomorphism from a braid group to a smaller braid group. So you send sigma 1 and sigma 3 to sigma 1, and sigma 2 goes to sigma 2. The braid relation is satisfied. You just check. There's 2 braid relations to check. So that's sort of a weird special thing. But for n at least 5, you don't have that special thing, and every homomorphism is equivalent to exactly one on our list. Any questions on the statement or anything else? Okay.
Sorry, okay, sorry, I do have a question.
Please, yeah.
Now I'm kind of confused by what you stated on B4.
Let me go back to B4, yes.
Yeah, so if you are mapping B4 to B3 like this, can't you just do something similarly funny with more strands?
No, amazingly you can't. This is yeah, amazingly you can try and it will fail. So for n bigger than well, that would be a counterexample to our theorem, right? But it was known long before us that I think it's Vladimir Lin proved that a homomorphism from a braid group to a smaller braid group must be trivial or have cyclic image, I guess. Actually, Lin proved something better. He said if you had a homomorphism from Bn to the symmetric group or n-1 or any smaller n, there are none. There are none, except cyclic image, because the braid group maps to the integers. That's the abelianization. And so you can have cyclic image, but that's it. And okay. So there's nothing. So that tells you. I'm not giving you the proof because it's hard, but I'll give you a little bit of idea of our proof. And maybe we can see where our proof. I won't give you many details, but maybe I can give a hint where it fails for B4. Yeah. So that's it. That's the theorem. It's a complete classification. Again, equivalent means up to transvections and post-composition by automorphisms. Okay, so let me give a word about how we go. The idea is to use torsion, which should strike you as funny because I told you the braid group was torsion-free. Okay, but braid group has elements that are like torsion. They have rotations. Okay, this is the braid group on 5 strands. That's why I put a 5 here. And basically the first braid is you should think of that first braid as, where should I draw it? Here, I guess, as this. Okay, that's kind of like a rotation. Okay, it has infinite order. If you multiply that by itself, it will never become undone. The other one's harder to draw as a braid, but the difference is in the first one, there's a strand, no strand in the middle. In the second braid, there's a strand in the middle. So these are not torsion, but they behave like torsion elements. Okay. Basically, if you mod out by the center of the braid group, these become torsion. That's the idea, right? Because the fifth power of this one is the central element, the full twist. And so modding out by the center, these are torsion. So you can recognize them as torsion. As it says at the bottom, the nth power of the first one and the n-1st power of the second one generates the center of the braid group. So the idea of our proof is to understand if I have a map from the braid group on n strands to some other braid group, you ask, where can this torsion element go? Okay, and because the center has to go to the center, you can mod out by the center. I think I say something like this on the next slide. Yeah. So let me say the, so those are the elements. Let me say a little bit about the idea. So again, the way you show that every homomorphism is standard is to rule out everything else. Okay. And we want to rule out that where can rho of alpha n go? Okay. And show that there's only a few possibilities. So that's that rotation. And this is maybe a lot of words on one slide, but this is the summary of the proof. Okay. So suppose you have a homomorphism from Bn to Bm, and suppose the GCD is 1. Okay. We want to show, so we're showing here, so let's say you're mapping B5, you want to understand B5 to B6 and show that all homomorphisms are standard. Okay. Well, then you ask, this rotation of order 5, where can it go? It has nowhere to go. If it goes, you might hope maybe it'll go to the rotation in B6. Okay, but then there's a simple number theory argument saying that can't happen. Okay, so here's the idea. If this were to happen, so we're assuming that the rotation of order 5 goes to rotation of order 6, well then some power of the image would be central. Okay, but the normal closure, so this is a key fact, which I won't be able to prove today. The normal closure of any of these rotations contains the commutator subgroup of the Braid group. Okay, and it follows from this that the entire commutator subgroup, because it's in the normal closure, has to map to the center. But the normal, the commutator subgroup is a big subgroup of the Braid group. But that's the idea. So if this torsion element went to another torsion element, then its normal closure, so in other words, a power. So in other words, in this case, the 6th power of this would go to the central element, right? In this case, the 6th power of this element would go to the full twist here. But then the normal closure of this element, which is so the 6th power of this is a twist by single click. Okay, and the normal closure of that has to go to the normal closure of the center, which is the center. But the normal closure here is big, and the normal closure here is small. That's the idea. I know that's a lot of information on one slide, but maybe it gives some idea. Any questions? Okay, well, that's all I'm going to say about that one. Well, let's see. We have a time. I'm going to tell you about the other theorem. So what was previously known was you're mapping the Braid group to the Braid group, and we changed the target to B2n. The goal here is to change the domain, make it smaller. Okay, so I've mentioned the abelianization before, but this is what it is. Given an element of the Braid group, you map it to Z just by taking the sum of the exponents, right? You write your element of the Braid group as a product of sigma i's plus or minus 1, and just take the signed word length. That's a homomorphism because you just check the Braid relation and the commuting relation are satisfied. And so this is just counting the signed crossing number of a braid. And that is the abelianization. Okay. So in other words, the commutator subgroup is the kernel of that homomorphism. So if I want to know, if I have a braid, I want to know if it's in the commutator subgroup, I just count all the signs with, count all the crossings with sign. If that's 0, it's in the commutator subgroup. So any question on that? Okay, I'll keep going. This is our second main theorem. Actually, it's a little bit embarrassing. So these are 2 separate papers, but we submitted both papers, and one of the referees pointed out that this theorem follows from the other theorem I already told you. But I still don't care. The proofs are totally different, and I like the proofs. The proofs are both interesting. So for this one, I want to emphasize the idea of the proof. What's the reason? Oh, let's see if so anyway, so let me state the theorem first. And it has to be at least 7. Well, it's also true for smaller n. Someone else proved it after us. Any row from Bn prime to Bn is either trivial or equivalent to inclusion. Okay, now there's no cyclic homomorphisms here because Bn prime is perfect, so it does not map into an abelian group. So here, there's no transvections. Because Bn prime is perfect, there's no transvections. So equivalent here just means post-composition by an automorphism. Okay. Right, oh, it says that there. Yeah, no transvections. This answers some questions of Vladimir Lin. They were all kind of the same question, just different stages. He asked about what are all automorphisms of Bn prime and what are all injective homomorphisms. But anyway, we classified all the homomorphisms. The reason this follows from our other theorem, let me see if I can remember on the fly. Maybe someone else can see it faster than me. So we want to understand homomorphisms from Bn prime to Bn. And the point is, we can embed Bn, there's a natural map from Bn prime to Bn plus 2. Is that what I want to do? No, that's not what I want to do. There's a natural map from Bn to Bn plus 2 prime. And then there's inclusion of that into Bn plus 2. Okay, what is this map from Bn to Bn plus 2 prime? You take a braid, and it might have word length non-zero, but then you add 2 more strands and twist those last 2 strands so that the word length becomes 0. That's this embedding. Okay, so you have these 2 maps. So if there was a weird homomorphism from here to here, as in our theorem, then you would have a weird homomorphism from Bn to Bn plus 2. And our first theorem says there's no weird homomorphisms from Bn to Bn plus 2. But anyway, so it does follow from our first theorem, but the proof is totally different. And I want to tell you about the proof idea. Okay. Oh, there were some prior results. Lin classified homomorphisms from Bn prime to Bm for m less than n. They're all trivial. Orevkov computed the automorphism group of Bn prime. And Maclay gave a new proof of Orevkov's result. And Orevkov also gave a new proof of our theorem very, very recently. And I didn't add it to the slides yet. Okay, so let's see. The proof uses a definition, which I think is new, which turns out to be very useful. It's something called totally symmetric sets. And we came up with it to prove this theorem. And then now there's 5 other papers, maybe 6. There's a bunch of other papers that use totally symmetric sets to classify homomorphisms between groups. Okay, so it's something just about groups. So here I have G as a group. X is a subset, not a subgroup, a subset of the group. And we say X is a totally symmetric set if the elements commute pairwise and any permutation of X is achieved by a single conjugation in G. Okay, so for the symmetric group, this is probably familiar. Well, it's not too unfamiliar. If you take the transpositions, sigma 1, sigma 3, you can think of those as transpositions in the symmetric group. Okay, those all commute, so they satisfy the first bullet. And if you give me any permutation of the transpositions, you can conjugate the symmetric group by a single element to achieve that permutation. Okay, so that's an example of a totally symmetric set. And in the braid group, you can take sigma 1, sigma 3. Right? We use the same notation in the braid group and the symmetric group for those elements. So any questions on the definition? This was the main innovation in the second paper. Other examples of totally symmetric sets would be in the general linear group. You can take the identity and put a minus sign somewhere. So there's n different elements like that. They all commute. And you can conjugate, given any permutation of those elements, you can conjugate, is that correct? I think so. Any permutation of those elements is just a permutation of 1 through n, which you can achieve by conjugation by that permutation matrix. Okay, so that's another example of a totally symmetric set. What's the point of totally symmetric sets? It's this. So here's the definition at the top again. It's this lemma. If you have a homomorphism, a totally symmetric set either maps to a singleton or another totally symmetric set of the same size. Okay, why is that? It's because if you have a totally symmetric set and two of the elements go to the same place, then by the symmetry, everybody has to go there. Okay, because if the first two are going to the same place, well, the first two are conjugate to the first and the third. And so since 1 and 2 are going to the same place, 1 and 3 have to go to the same place, etc. So you should think of this as like Schur's lemma from representation theory. It's like an irreducible representation either has to go to another irreducible or trivial. And so the way, well, any questions on the statement of the lemma or the definition here? Okay, so well, here's how you use the lemma. So in the Braid group, we have totally symmetric sets, the sigma 1, sigma 3, sigma 5. And so if we can classify all the totally symmetric sets of that size, right? So in this case, if they all go to a singleton, you see that your map has a cyclic image. Okay, so the other case is it goes to a totally symmetric set of the same size. So if you can classify all the totally symmetric sets, then you start to understand your homomorphisms. That's how these go. So in the Braid group, it turns out you can classify all the totally symmetric sets of size and floor of n over 2, and it uses Nielsen-Thurston theory. Okay, and Bn prime also has a large totally symmetric set. So we use this totally symmetric set in Bn prime. It has to map to a large totally symmetric set or a singleton. And because we can classify them, you have a very good control.
What is Nielsen-Thurston theory that you, what he says the Nielsen-Thurston theory here?
So Nielsen-Thurston theory says that if you have a mapping class, so like Braid, again, we think of braids as mapping classes. Nielsen-Thurston theory says that any mapping class has a reduction system. So some collection of curves that's fixed, okay? And it says on each piece, you're either periodic, so like one of these rotations I showed you, or pseudo-Nosov. Now, I can't tell you in just 1 minute what pseudo-Nosov means, but the important thing about pseudo-Nosov is that if F is pseudo-Nosov, the centralizer of F, what's the symbol for centralizer? C of F is cyclic. In the case of the Braid group. In the case of the mapping class group, it's virtually cyclic. So that's how you use it. You basically break up into pieces, and each piece you understand. Also here, the centralizer is also cyclic, usually. That's not that one's a little bit more complicated. But the point is, it's like a Jordan normal form for a mapping class, where it breaks it up into pieces that you have pretty good control over. And so this is actually kind of hard to do, not too hard, but it's using those ideas. Yeah, yes. So that's basically how the proof goes. I won't go into much more detail or any more detail, but you classify these totally symmetric. That's the kicker, is that you can classify them. So I'll just say another word just to show you this idea of totally symmetric sets has been used a few times recently. So this was a group of undergraduates plus my postdoc, Kevin Kordek. I asked them a question. Amazingly, it's not known. What's the smallest quotient of the Braid group? Okay, we know that we have the smallest finite quotient, smallest non-cyclic quotient. Okay, so we know we have the Braid group mapping to the symmetric group. Is that the smallest one? And if that was true, the quotient would have size at least n factorial. So they got partway there. They showed the quotient is at least this number, which is less than n factorial. So that's part of the way there. And two of the undergraduates also classified totally symmetric set. In a free group, a totally symmetric set has size at most 1. In a dihedral group, it's, I think, size at most 2. Solvable groups, it's size at most 4. So that allows you to control homomorphisms between groups. I think I have a picture here. This is Caleb and Lily and Alice. yeah, that's their project at the joint meetings. And two other recent papers. So Kaplan and Kordek proved or answered my question for n equals 5 and 6. The smallest non-cyclic quotient of B5 and B6 is the symmetric group. And this last one is a paper I received in my email last night, which they use the same idea of totally symmetric sets, not to go from braid groups to braid groups, but braid groups to mapping class groups of closed surfaces, which we mentioned at the beginning. I think that's it. Oh, there's a connection to polynomials. If someone's curious, I'm happy to explain. But I'm going to stop there since we went a little bit over. Thank you guys for your attention.
So let's thank again the speaker. Please unmute your microphone. Now, ours for some questions. Somebody has questions? Other questions? Comments? Please.
Well, I asked several questions, but I have another one.
Sure.
Is it known whether braid group is coherent?
Oh, good question. So coherent means that finitely generated subgroups are finitely presented?
Exactly.
Don't know off the top of my head, I think. Let's see. Oh, I don't know off the top of my head. It's a good question. I should know. What's do you know do you know what the simplest example of a incoherent group? I could wonder if that's a subgroup of the braid group.
I think F2 cross F2 is not coherent.
Oh, okay. Well, F2 cross F2 does embed in the braid group. So the way you do it is, because remember these pseudo and Alsop pieces have the property that they don't commute well with other elements. And so, oh, there's even a simple thing. If you take this Dane twist and this Dane twist, okay, so just take the full twist about each of those strands, those generate a free group. And so if I have enough strands, I can do the same thing over here. And so we have a free group on the left and a free group on the right. And since the left side.
And they commute?
Yes, because so this is a free group over here, and this is a free group here, but they commute because there's no interaction, right? If you do a homeomorphism on the left side, the surface is divided here. The homeomorphism on the left side, or if you think of it as braids, there's no interaction, right?
So the answer is no.
So the answer is no, yeah.
Thank you.
Yeah, thank you.
More of the question?
I have a question then. Those results on the smallest quotients of the braid groups. I mean, there's a not sure if I can call it recent, but there were some results by David Kielak, Emilio Piero, and Barbara Baumeister. Yeah. So first on the smallest quotients of AutoFN, and then on mapping class groups. So is any of that used in the?
No. Yeah. So that's the amazing thing, because the mapping class group should be harder. So the analogous question for mapping class groups is known, and you already just said the list of authors. So for a mapping class group, the mapping class group acts on the mod2 homology of the surface. So that's a finite quotient. It's not cyclic. Well, it can't be cyclic, and that's the smallest one you can think of, and that's the answer. And amazingly, for the braid group, the analogous question was never asked, and but they don't use any of their work. The way they do this is they use the classification of finite groups and kind of go through and exhaust, and they use the totally symmetric sets. But yeah, this is a very tantalizing question. But yeah, so far that's the progress.
May I ask something else? So, okay, this is maybe not a proper question, but I'm just thinking about wild stuff to do. So since you are we are looking at let's say organizing homomorphisms between braid groups of various orders. Does it make sense to look, for example, at the braided version of Thompson's group V, where you get all the braid groups embedded inside it, and then, I don't know, do funny stuff, and then get some information about homomorphism between them?
So is your idea that you can make in more different non-geometric homomorphisms by first embedding into Thompson's group? A great question. So, okay, I think the conjecture is, actually Lei and Kevin and I conjecture in our paper that they're all geometric, in the sense that a homomorphism from Bn to B whatever, large N, is iterated cabling. So you can kind of iterate the cabling process if you have enough strands. That's the conjecture. So yeah, if you can make a counterexample, I never thought about that. I don't know much about Braid and Thompson's group, but if you can make a counterexample using that, it would be very interesting.
Okay, thanks.
Yeah.
Some other question?
Oh.
Yeah.
Yes.
These operations of the brain is an idea that there's some automaton active. The question is the braid group generated by finite automata?
Yeah. Let's see. I don't know. I have to think if I know I believe the answer is yes. So definitely the normal closure of one of these rotations is the whole braid group. So I guess that means that the braid group is generated by conjugates of the rotation. So therefore the answer is yes. So basically you can take your favorite one of these isometries or rotations, and you need some number of conjugates of this to generate the braid group. But the answer is yes. I think this has been known for a long time, but in our paper we actually talk about this. The paper with Lei Chen and Kevin Kordek.
Well, so this would be an automaton of more or less what degree?
Do you get an automaton? I'm not sure. It's sort of it's a great question though. I don't know. That's a great question.
How do you interested in a reference?
Oh, sorry, could you say that again?
How do you interested in having a reference?
Oh yeah, I can send you a reference for sure.
Thank you.
Yeah.
Some other questions? I have a question. My question is do you know something about, I know that the Braid group is residually fine, so it's interesting to ask some more residually question about this group. So do you know something about the profinite completion of the Braid groups?
I personally do not, but so there's been a lot of work on profinite completions of mapping class groups. Right, there's something called the congruent subgroup problem, which is, the goal is to understand all finite index subgroups of the Braid group, and they all are supposed to contain a congruent subgroup. And so Bill Thurston gave a proof of the congruent subgroup problem, and the paper was written by Ben McReynolds.
But wait a minute, if you talk about congruent subgroup problem, you mean a classical congruent subgroup problem when you see it as a subgroup of a linear group?
No. So for mapping class groups, when we say congruent subgroup problem, like the classical version is wrong, like for mapping class groups. So a congruent subgroup is you take so you want to list some finite index subgroup, right?
I understand. It is about in terms of automorphism.
No, it's not. Well, you can phrase it in terms of automorphisms. I always think about it as covering spaces. You take a covering space of the disk and take the braids that lift to the cover. Those are congruent subgroups. Mm-hmm. But there is a way to say it in terms of automorphisms. Yeah, you map. So I guess the Braid group maps to automorphisms of the free group, and then you mod out the free group by a characteristic finite index characteristic subgroup, and take the kernel of that. So those are basically the same, almost the same thing. But that's the way.
I know in the following terms, that you take first profinite completion of automorphism groups, and then you make automorphism group of the profinite completion. And the question is whether one embeds in the other.
I see.
So
I see. I don't know if that's known. I don't know if that's...
It is something similar because it boils to the really to characteristic subgroups. I mean, of finite index, of course.
Yeah, I see. So I don't know the answer. Yeah, I don't know exactly what's known. McReynolds' paper is related, and there's some work of Boji on the congruent subgroup problem and the profinite completion. I don't know exactly. I'm not sure exactly what's known at this point. The congruent subgroup problem is definitely open. That's one of the top couple open questions for mapping class groups. But the Braid group case, I'm unsure.
Is there a variation of, or maybe, okay, is there something with the definition of those congruent subgroups? Do they have any relation with, let's say, congruent subgroups of in the Borel representation?
I don't know what those are.
So yeah, I mean, so the Borel representation where you send the Braid group to well, something inside GLN.
Oh, Borel representation. Oh, sorry.
Yeah.
So that gives you there's a connection. All of those congruent subgroups are examples of the more general kind. So, but it's not enough. The congruent subgroup problem would be false. It's not true that every finite index subgroup of the Braid group contains one of those. Yeah, but to get all of the congruent subgroups, yeah, that's all I know, I guess. Is that those are examples, but it's not enough.
No more questions? If no, let's thank again the speaker.
Thank you guys so much.